So my name is Matthew, and this is my session 2 assignment. So within this assignment, we're given the task of having a client, and we're a financial advisor, and our client is 23 years old, and he's making 65,000 a year, and he plans to retire at the age of 65. His goals are to save 30% of his income annually. So we're going to set the inflation rate to be 2% per year, and the interest rate at 5% per year. So we also expect the salary to increase by 3% maybe per year as a fixed constant. So one of the first things we could suggest was a 60% savings being going towards stocks and 40% going towards bonds, with the stock to return at 8% per year and the bonds to return at 4% per year. The goals in this thing is to be able to figure out how much we have at 65 and the present value of the amount. In addition, alternative investment plan, as well as how much money he would have if he ended up investing 1,000 more at the end of every year. So with this, we can take a look at the code and the analysis. So the first thing I did was to import our necessary libraries like pandas, the NumPy, Matplotlib, and Seaborn. From there, what I did is doing the first step of the framework would be to define your variables and the information that's needed. So I have the goal being the project future the future value of the client's savings as he would have at age 65 with his current investment strategy. Information needed to complete this analysis would be all the info provided in that problem statement that I just read off. So age, salary, savings rate, inflation rate, interest rate, return rates, your investment rates, and your increase rate. So the action in this would be to utilize the provided variables to calculate the present value of investments at the age of 65, initially vested at the age of 22. So as you can see here, I have all what I just said with the variables and different factors listed here to start out. So moving on to the next portion of the analysis would be to calculate our weighted average return of the portfolio mix that we have. So here you can see the formula is just your weighted return equals your stock investment rate, multiplied by stock return rate plus your bond investment rate times your bond return rate, and it ended up being 6.4% for our annual return on the portfolio mix. Next on, we can move on to our implementation phase, where we calculate the future value of the client's savings. From here, we can initialize our variables like total savings, yearly salary being set equal to current salary, and your years to invest being equal to your retirement age minus your current age. So first thing we want to do is create a list so we can store the data that we use to visualize later. And through here we can have a loop, a for loop set, for each year of saving. Now, as we go through here, you can see the different formulas that were used through the loop itself, such as, for example, yearly salary equals yearly salary times, in parentheses, 1 plus your salary increase rate. So now we have all these listed here. We can move on to calculating the actual present value of this amount. So the formula you use here for the present value is going to be your total savings divided by, and then in parentheses, 1 plus your interest rate raised to the power of years to invest. So after we have that formula set and we have it concrete, we can move on to creating that data frame for the annual data for this analysis, being DF savings. So at the end of this, what would be the total amount of money if we had the initial investment strategy of 6% going towards stocks and 40% of the savings going towards bonds? Well, the client would have roughly 2.6 million at the age of 65. And calculating that to be for present value, that's the equivalent of roughly $763,000. So now we have that listed and we've knocked it out of the way, we can move on to an alternative plan that we could suggest to our client, which would be an aggressive split, more aggressive than what was previously listed that we just went through. And this would be 80% going towards stocks and the rest of the 20% of the savings going towards bonds. So now we have it listed as 0.8 and 0.2, we can move on to figure out our new weighted return, which is going to be the same kind of formula that we had previously, just with a new variable name being alt in front of the weighted return. So once we have that listed and set, we can rerun the simulation and go through another for loop, same similar process that we just had. And after that's out, the output will spit out that it is better to adopt a more aggressive, the 80% stock, 20% bond allocation over the 60%, 40%, stock bond allocation. The reason for this is because this new allocation increases the weighted return to 7.2 over 6.4, which will in turn yield us more money in the long run. So with this plan of this 80-20 split, the client will have 7.57, give or take, million at the age of 65, which is over 1.37 or 357 million over what he would have at 65 if he did the 60-40 split. So an additional scenario that you need to take into account is what if the client wants to add $1,000 extra annually? So for this, we're going to again run the same for loop, same formulas, but this time we have the addition of the the $1,000 added onto the end of it being added yearly. So how would this affect the total outcome for what we have at 65 after 43 years? Well, he would have 6.4 a little more than 6.4 million at retirement, and this is an increase of about $209,000 from the original plan of that 60-40 split. So now that we've gotten those three scenarios out of the way and we've analyzed them, we can now validate the process itself to see if it's correct. And moving on to this 401 calculator that I looked up online, when we put in our numbers of 65,000 being our annual salary, 30% contributing, how much we're contributing a month from our savings, a salary increase of 3% a year, being 22 years old and retiring at 65, we're going to use that portfolio mix of 6.4. This is for the 60-40 split. We have zero money currently in the bank. We're going to do a 0% employer match and a 0% salary limit for employer match. So this comes out to be about $6.28 million at 65 after 43 years, which is pretty close to what we have already. Being where is the number? That's 6.216. So I'd say that our model is pretty accurate based off of that. So now coming back to the evolve section, of the framework. Excuse me. So with purchasing power, we can take it a step further and calculate what would the purchasing power of that 60-40 split be in today's money. So when you have this, we have the final nominal value equaling the total savings, and to discount the future value by the inflation over that 43-year investment period, we set the purchasing power today equal to the final nominal value divided by, in parentheses, 1 plus inflation rate raised to the power of years to invest. So now that we have all this output, the end output would be that the client's nest egg will be 6.216 at age 65, but since we're accounting for that 2% inflation for that 43 years, the purchasing power in today's money, when he'd be 22, if he had that money transported from when he's 65 to 22, it would be roughly about $2.65 million. Now that we explore that option, we can do a little bit of reflection on this analysis itself. So, after completing the time value of money analysis, there are a few takeaways that can be made from this. The first one being, since growth of just compound interest is exponential, the last 10 to 15 years of the client's portfolio growth will provide the largest growth in money in terms of, how much from start of the decade to the end of the decade will have the biggest growth. So because of this, it can be said that, the length of time, in this case, it being years, is a top contributor to the investment's growth when dealing with compound interest. In addition to that, out of those three investment options, the 60-40, 80-20, and the adding of $1,000 annually, the 80-20 split will add about that much to the time of his retirement versus 6.216 million with the 40 split having 6.426 with the addition of $1,000 annually. Thank you.